Hello, we continue with contour integration. Today a very famous integral, the integral from 0 to infinity of sine of x over x, which is well known to be pi over 2. Well, the most common technique for actually evaluating this integral is just introducing some kind of factor to reducing factor e to the minus something and do it by differentiation under the integral sign, but today we're going to do it by complex integration. Okay, so the contour that we're using for something like this, first of all, let us note that what function we'll be using in order to do this particular integral. We'll decide on the contour in a second, but the function, we're not going to leave the sign in there. It's much easier to work with exponentials, quite usual stuff. So we're going to use e to the iz over z dz, and let us know this particular function has a pole at the origin, so we're going to get the minus infinity to infinity, which eventually, this being even, we're gonna reduce to 0 to infinity. So we need to use the real axis. This is where our integral is gonna come out of, but let us know we have a pole at the origin, and therefore we're gonna use a semicircular contour of radius r, so minus r to r, but we're going to indent it at the origin, so another semicircle here. So this bit, if you want, is not part of our contour. We're going round it in an anti-clockwise direction, so we're going to transverse it in this particular fashion, so no poles inside our contour as we have it in there. Oh, by the way, I forgot to put the radius of the smaller circle, typically for small things, minus epsilon to epsilon. And probably a good idea to label a few bits. The whole thing, we're going to call it, of course, let's say capital gamma, and the two semicircular arcs, let's say we call this one a gamma 1 and this one a gamma 2. So we're ready to go. So by the residue theorem, if you want, or in this particular case by Cauchy's theorem, because there are no poles inside our contour here, this particular integral around big gamma should of course produce 0. So we're going to split this particular contour now into two straight line segments, the semicircular arc around gamma 1 and around gamma 2. So I'm going to do that here somewhere. So the integral around from minus r to minus epsilon plus the integral around gamma 1 plus the integral from epsilon to r plus the integral around gamma 2. Let's put a little curly bracket here of f of z, where f of z is of course all of that dz should give me 0. I'm going to just rearrange it a little bit. I'm going to just rewrite the integrals and I'm going to start putting things in. So first of all, I'm going to put the integral along this straight line section, first of all, from minus r to minus epsilon. And for this particular section, the parametrization I'm going to use for my f of z, this is my f of z. Let me just put it in red. So this is my f of z when I'm referring to it. So the parametrization, of course, that I'm going to use along the x-axis, quite clear. Along the x-axis, z is equal to x, and dz is, of course, the same as dx. So along the straight line segments. So I can write my e to the I z over z as e to the I x over x dx, and similarly I'm going to write this integral next, which is very, very similar, e to the ix over x dx, but with different limits, and the limits of course are now from epsilon to r. Next I'm going to write, let's say, the integral around gamma 1. Gamma 1 is the small circle, small circle. Shall I just parameterize it at this stage, or shall I just leave it as it is? Let's leave it as it is for the time being. E to the iz, we're going to think about how we're going to deal with that, over z dz plus, I'm going to do the same thing up for gamma 2, which is the big arc, e to the I z over z dz, and of course all of this should give us 0. What's the plan now with all of this? The plan with all of this is to eventually let r go to infinity and epsilon go to 0. So essentially we'll be shrinking this particular circle into nothing, and we'll be blowing this circle forever, but of course we'll be extending the x-axis to the left and to the right, and hopefully get a desired integral out of these two bits here. So first of all, we're going to deal with this, the integral around gamma 1. Let's make a bit of space, because I don't want to write at the bottom of the board. So the first two integrals at the moment, I'm not going to do anything. I'm just merely rewriting them. E to the ix. Loads of writing for this particular work, very annoying sometimes. Lines and lines of workings just to make one little change sometimes, which is very annoying. Okay, so let's parameterize a little bit this gamma 1. So along gamma 1, so I'm going to do it here, our z is going to be epsilon, that's the radius of the circle, e to the I theta, and let us know that our theta will run, because we're going from in this direction, we're going to start from argument pi, or not argument, but from angle pi in the parameterization, from pi to 0. So it runs from pi to 0. And of course we need r dz. R dz is going to be, I have to be very careful, I often mix my epsilons and the e's, so watch me for this. It's going to be epsilon I e to the I theta d theta. Let's write it in z as well, probably be easier with the cancellation. So it's going to be, I don't know even why I wrote the I next. E to the, all of this is my z d theta. So let's see what happens to this particular integral. That's around gamma 1. The limits now are from pi to 0 once parameterized. The e to the iz is going to be a mess. It's going to be e to the I epsilon e to the I theta. I'm going to leave this z as it is because I have moved z into my dz. So it's going to be iz d theta. So that would nicely cancel me there. Okay, so I'm up to gamma 1, and unfortunately I don't have space for my gamma 2 there. I'm just going to make a little bit of room here. This actually we don't need it. Let's just check that everything is okay there. We haven't made any silly errors or something. I'm going to wrap this off as well. And I'm going to put the last integral, which is around gamma 2. And I'm going to leave it as it is, this particular one. Why don't I parameterize it? Maybe you can see why not. I'm going to use Jordan's lemma for this when it comes to it, when I let obviously r go to infinity, and this will vanish, this particular one. So I don't want to do anything with that. It would be a total waste of time. So dz is equal to 0. So far so good. So now I need to look at what I've got up there, and whether I can take limits or do I need to do more work. Sometimes I have to do estimations and see what happens. Now, this particular integral, this will not be a problem. These two actually will produce what I'm after up there once I let r go to infinity and epsilon go to 0. So these two integrals that I'm really looking at. This one, it satisfies the conditions, as I said, for Jordan's lemma. So if I let r goes to infinity, that's the big one, the big arc, it will vanish because it is of the form e, that bit here is of the form e to the I a z, where I is real and positive. In this case is 1, multiplied by some other function, which in this case is 1 over z, and so long as this function vanishes as the modulus of z goes to infinity, r goes to infinity on this particular type of arc, from minus r to r. This satisfies Jordan's lemma, so once I take limits, this will be gone. It's this one here now, and we got to think what happens in there. Well, this, of course, the limiting case is when epsilon goes to 0. When epsilon goes to 0, I don't know if you can see it from here. We're going to have an I there. Okay, that's not a problem. Let's move the I actually to the front so we don't lose it. We have epsilon on the exponent, and if epsilon goes to 0, that's going to be e to the 0, which is 1. So essentially, we'll be integrating 1 with respect to theta from pi to 0 with an I at the front. And of course, normally if it was 0 to pi, it will be producing pi I, but of course, because the limits are the other way around, this will give us minus pi I. If you're not happy with that, then you might be thinking funny things might be happening in there. It's a little bit tedious, but I'm just gonna put a bit of working in there if you want. So we can write this quantity as an expansion. This is the exponential function, so it's e to the I epsilon I theta. I have to be careful now because that looks very, very messy. It's going to be 1 plus I epsilon e to the I theta plus I squared epsilon squared e to the 2I theta plus I cubed. I'm going to put the factorials in a second. We got I cubed epsilon cubed e to the 3I theta. All I'm doing is the exponential the exponential series, so that's over 2 factorial over 3 factorial, so on. And if you look at all of those terms, the e to the 2I theta is just sines and cosines, so that's going to be the terms are of the form e to the let's do one at a time perhaps. Cos theta plus I sine theta. This is this bit here between the limits of pi and 0. So this produces, first of all the imaginary parts, 0 and pi, will be vanishing, and you're going to be getting ones and minus ones. I don't think they'll be cancelling, because it's going to be getting, from this particular one, 1 minus minus 1, so it's a 2. So this is 2, but of course, once you let epsilon goes to 0, it'll be vanishing. Similarly, for the next term, okay, you're going to have a minus 1, that's from the I squared. You're going to have epsilon squared. You're going to have a 2 factorial, who cares? And this is going to be 2 theta and 2 theta from the e to the 2 to the e to the 2I theta. But again, okay, this bit's pi and 0, goodbye. And then the cos of 2 theta, at 0, it'll be giving you 1, and at 2 pi, we'll be giving you minus, we've got 2 pi now, so it's going to be also minus 1. So they'll be vanishing, anyway, it'll be 0. So they'll be getting alternating terms that will be having contributions, but because of the epsilons at the front, once you let the epsilons go to 0, the only thing that will survive is that nothing funny is happening with this bit here, because we got other bits from the e to the I theta. Okay, so if we let now epsilon goes to 0 and r go to infinity, let me just clear all of this so we can see the very last line we reached. So that plus that plus that plus that is equal to 0. We have the following. This integral is going to go from minus infinity to 0 e to the ix over x dx, and similarly the other one, 0 to infinity e to the ix over x dx. This one we're going to have plus I, and as epsilon goes to 0, we're going to get pi to 0 e to the 0, which is 1 d theta, and this last term vanishes by Jordan's lemma as r goes to infinity, and therefore this is my latest line that I've got after all these calculations. I can combine these two integrals now, because minus infinity to 0, 0 to infinity, identical integrands, so I can actually put them together as the integral from minus infinity to infinity e to the ix over x dx. And notice, because we're going obviously the wrong way, we're going from pi to 0, this integral will produce a minus pi, so this item here is equal to 0. Let's make a little bit of room, and I think we'll have our answer now within 3 lines. All the main work has been done. So we're going to have, I'm going to do a couple of things at once. I'm going to write minus infinity to infinity, switch now into real and imaginary part. E to the ix is of course cos x plus I sine x over x dx, and shove this to the other side is I pi. Splitting the integral now. First of all, the cos of x over x is odd in a symmetrical domain. There's been no contribution, but of course we can see that because there's no real part in there. So we're only going to have minus infinity to infinity I sine x over x dx is equal to I pi. And of course we can get rid of the i's on both sides, and this now is an even function, so 2 lots of sine x over x dx should be pi, and then divide your 2, and we have the desired result. It's not too bad. It's obviously a lot better and a lot easier if you use differentiation under the integral signs, but I hope you followed what I've done up there, and you're getting something out of these lectures. I truly hope it's educational, and who's laughing now?